statistics about car crashes. 1.3 million people are killed each year due to car crashes, with another 20 to 50 million people injured. Car crashes account for 2.2% of all deaths worldwide and is the number one killer of young people. In fact, over 1,000 young people are killed daily due to car crashes. Cars have many safety features intended to protect its occupants in the event of a crash. Airbags, seatbelts, and crumple zones attempt to reduce the deceleration experienced by the passengers in order to lessen the chances of injury. Brakes obviously slow the car down to prevent an accident in the first place. Finally, a safety cage prevents the car from rolling over, possibly injuring the occupants if they fall out of their seats. The braking time of a car is composed of two times: the reaction time of a driver and the time taken for the car to actually stop. The reaction time of a driver tends to be around 1 second. The stopping time of a car depends on the velocity of the car and of the braking acceleration of the car. The braking acceleration of a car tends to be around 4.5 meters per second squared, or around half g. We can use the braking acceleration of the car combined with the velocity of the car to give us the stopping time of a car, which is the velocity divided by the acceleration. From there, we can do some calculations to figure out the average time taken for a car to stop. On the right, you can see the calculations. Given that the car is moving at 60 km per hour, the driver's reaction time is 1 second, and the acceleration of the car is around 4.5 meters per second squared. We will now calculate the braking distance of a car. Let TR be the reaction time of the driver, and TS be the stopping time of the car. The braking distance is the reaction time of the driver times the original speed plus the stopping time of the car times the average velocity of the car when it is decelerating, v by 2. Simplifying, we obtain the following equation. We will now consider an example. Consider a car moving at 60 km an hour, or about 17 meters per second. An average car has a braking acceleration of negative 4.5 meters per second squared, with a driver's average reaction time being about 1 second. Using the braking distance formula, we can calculate the braking distance required to be about 15 meters. This means that if a car is moving at 60 km an hour, and an obstacle is sighted by the driver, which is more than 15 meters away, the driver can stop safely. However, if the obstacle is closer, the driver may not be able to stop in time. The frictional force exerted on the car by the ground is proportional to two things: the static frictional coefficient between the tire and the ground, and the normal force exerted on the car by the ground. The normal force is equal to mg, as we know. Therefore, we have the force equal to mu times n, where mu is this frictional coefficient. Rearranging Newton's second law, we can work out the acceleration due to friction to be mu times g. Finally, we can substitute into our braking distance equation in order to obtain the equation in terms of only the velocity, the frictional coefficient, and the force gravity. Many deaths and car crashes are caused by large accelerations, and large accelerations occur when we have large forces. The change in kinetic energy during a crash is equal to the net work done by the net forces, which is the net force times the distance. This implies that acceleration, which is proportional to force, is equal to the change in work divided by the distance. This tells us that net acceleration is inversely proportional to distance, and so a longer distance in which a crash occurs means that the risk is less as acceleration is reduced. Airbags and crumple zones work by increasing the distance over which a crash occurs, thus making the crash safer for the occupants of the car.